Hey there, welcome back to 2241. This is the examples 3 video, and we'll pick up where we left off at problem number 10 right here. All right, so it says find the equation of the plane tangent to this function at this point. So first off, it's probably a good idea to check just that they gave us the correct point. And let's see, does 2 times 1 squared plus 1 squared equal 3? Yes, it does. And so we're happy with that. All right, cool. So they gave us the correct point and things work out. So let's zoom in here a little bit and start trying to find the plane tangent to this graph. So we need, first off, to write down that equation. So z equal f of a, b, plus fx, also of ab, times x minus a plus fy at ab times y minus b. Okay, and so we need to identify a few things here. So first off, we know what f is. That's this function over here. And what are a and b? A and b come from the point P, so they're the x and y coordinates there. So a equals 1, and so does b. All right, well, we can get f of AB pretty quickly because that's also given to us right here. So then we have f of 1, 1 equals 3. Cool. All right, now the other thing that we need is our partial derivatives. So we need partial z with respect to x, and that's going to be 4x, and the partial of z with respect to y is 2y. All right, next we plug in our points. So fx of 1, 1, I'm switching derivative notations a lot here so that we get used to it, is 4. Fy of 1, 1 is 2. All right, and that is enough to write down the equation of our tangent plane. Z equals 3 plus 4 times x minus 1 plus 2 times y minus 1. And if we wanted to simplify that to the standard equation for a plane, we would write 4x minus 4 to y minus 2, and bring everything with a variable to one side. So let's put 4x plus 2y minus z equal to let's see, 3 plus negative 4 plus negative 2 is going to be negative 3, I believe. All right, and that should be enough to get us the normal vector. So I'm doing a little bit extra at this point. Our normal vector is 4, 2, minus 1. And another thing that we can do here is just check that we actually get a normal vector in the same direction as this one by crossing the vectors from the derivatives, so our tangent vectors. Our tangent vectors are going to be ux, that is, let's see, so that's going to be 1 in the x direction, 0 in the y direction, and then fx of 1, 1. Okay, so that is, where is that? That is 1, 0, 4. And then uy, 1 or 0 in the x direction, 1 in the y direction, and fy of 1, 1 in the z direction. So we get 0, 1, 2. All right, and then we take the cross product of these two things, and we get, remember how our cross product works, 0 times 2 minus 4. Okay, seems odd. That's not the correct number. And then 4 times 0 minus 1 times 2 is negative 2. Right, that's weird. And then last, 1 times 1 minus 0 times 0. And we get positive 1 there. Okay, so it seems like we're getting this as our normal vector. So what's happening here? Well, the thing is that this normal vector came from rearranging this equation. And so it's not necessarily exactly the normal vector that you're going to get out of here, because I could scale this equation by, I don't know, 4 or -7 or something, and get different numbers here, but they would still be representative of the normal vector of this plane. It has to be the same plane if I multiply both sides by the same number. So what's happening here is that this, let's call it not n, but maybe m. So m is clearly the negative of the vector n. So we have normal vectors in different directions. And that corresponds to just a choice of positive direction for the tangent plane. Okay, so that's problem 10. Next, let's look at problem 11 here. It says, show that f of xy equal to x e to the xy is differentiable at 1, 0. Then find its linearization at 1, 0 and approximate this value, where you plug in some slightly different numbers. Okay. So to start, we want to get our derivative here. So we'll try to take the derivative of this thing and see, all right, does this thing look continuous? All right, so we need our partial f, partial x. That's going to be product rule here. So we have e to the xy plus x times y e to the xy, or 1 plus xy times e to the xy. All right. Next, we have partial f with respect to y, and that is going to give us, well, okay, now x is a constant, and so we just get x squared e to the xy. All right, so those are our partials, and the linearization, as I mentioned before, is literally just the equation of the tangent plane. So we'll call it L of f at 1, 0. Here's the function, and here's the point. That's what the linearization depends on. And I guess if I'm being perfectly honest, we're also saying that this depends on x and y. So the notation's a little weird, but I'm just going to ignore the x and the y for now. All right, and so we need the value of f at 1, 0. Okay, well, that's not too hard to compute. If I plug 0 in for y, I get an exponent of 0, which means this whole factor is 1, and then I put a 1 there. So f of 1, 0 is 1. You can write that down as well. F of 1, 0 equals 1 e to the 1 times 0 equals 1. All right, now we have our derivatives, and we can just go ahead and plug 1 and 0 into them. 0 will kill this term, and again, make this a 1. So that is a 1. And we have x minus 1, because again, a is 1, plus, now the derivative at y evaluated at that same point. Put a 1 in here, 0 in here, again, we get 1. So all of these derivatives ended up being very nice. And then we have y minus 0 here. All right, so now we clean things up by just erasing those 1s, and we've got the equation of our linearization. So now this is a linear function, and I can write it a little bit more simply if I want. I don't want to for a specific reason, because now I'm going to compute f of 1.1 comma negative 0.1 by saying, all right, this is approximately equal to L of 1.1 comma, minus 0.1. And here I've swapped the input notation a little bit. Now this is x and y. And L is implicitly dependent upon f and this point. Okay, so now I just plug in those numbers to this formula right here. And I get 1 plus, and here's why I didn't want to rewrite that, 1.1 minus 1 plus negative 0.1. Okay, and this is 0.1. So that makes our lives very easy, because now both of these second terms, or the second and third term, cancel each other out. And our final answer is that f of 1, 1 is approximately, or 1, 1, negative 0.1 is approximately 1. If we want, we can go ahead and compute this on our calculator. So let's see what our calculator says for 1, 1, comma, minus 0.1, about 0.9854. I like to get 4 decimal places there. There's no specification. Okay, and that is pretty darn close to 1. If we wanted, we could use a Taylor series expansion. This is basically a Taylor series expansion, but only to first order. And later on, we'll talk about how to get Taylor series expansions in multiple variables. Okay, so the error here is 0.9854. This is about 0.146. And that is pretty small, about close to 1 in 100 percent, or 1% error, I suppose. All right, so that's how we get linearizations. Let's do a slightly different version of that. Here, we're going to use a table. So we don't actually have a function given, but we want to find a linearization of the heat index as a function of T and H, the temperature and the relative humidity. So how does this work when we don't have a function to take a derivative of? Well, we can approximate the derivative itself. So let's write this down again. L of TH is going to be equal to I of 96 and 70 plus di dt, also at 96 and 70, times t minus 96 plus di dh 96 and 70, finally times h minus 70. Okay, so there's a lot going on there, but we can go ahead and do some estimation now. So what do we need? We need the value of I at this temperature and humidity. That's given to us right here. So 96, 70, 125. So we'll write that down. Okay, this is exactly 125. And now we need approximations to di dt at 96 and 70. And this is a little bit trickier. So how do we do this? Well, what we can do is use nearby values to approximate the change that's happening there. So I have a change of 2 in either direction here. And what is the change in temperature at this humidity? Well, it's 5 and 2 is 7 in the backwards direction and 8 in the forwards direction. So we have 2 different approximations here. Let's write these down. So we've got, what is that? 125 minus 118 divided by 96, or 90, yeah, 96 minus 94. Okay. And we also have 133 minus 125 over 98 minus 96. So this is just the average slope between these 2 points. I've written it in this strange way because we're going to do something to make our approximation hopefully better. We're going to take the average of these two measurements. So we get one value, we get another value, one above, one below, and hopefully the average is going to be a little bit closer to the actual value. So this is one way to get the derivatives. So let's see, we have, that's a 7 on top and a 2 on bottom. That's an 8 and a 2 on bottom. So we have 4 and 7 over 2. Well, actually 7 plus 4 is 11 times 2. So we have 11 over 2 here. All right, so we do the same thing for di dh. And this time I'm just going to leave the inputs unwritten because they're the same and I don't want to write them. But this time we're going to go in the horizontal direction because now the humidity changes in that direction. So we're starting at 125, looking backwards, and we get, we're still going to do our average thing, 125 minus 121 divide by 70 minus 65 plus 130 minus 125 over 75 minus 70. Okay. And if we go ahead and compute these, that's 4 over 5, that's 5 over 5, and so we get 9 over 10. Okay, so those are going to be our approximate derivatives. And so we're going to write down a linearization here. Maybe we'll call it L tilde because it's not the exact linearization, because I don't know what I exactly is. But this will be 125 plus my t derivative, 11 over 2 times t minus 96 plus 9 over 10 h minus 70. Okay, and so that's it. That's all we needed to do here is find this linearization. So it says find a linear function approximating. It doesn't have to be exact. It doesn't have to be exactly the tangent plane, but it's close, hopefully. All right, so this is how you work with imperfect information. All right, next page. We have 2 more problems to work out here. Once again, using linear approximations, but this time we're going to do total derivatives. So the total derivative of z here is this delta z thing. Well, actually, I guess if we're doing the total derivative, it should be a dz. Let's write delta z here is partial z partial x delta x plus partial z partial y delta y. Okay, so I need those partials and I need my delta x and delta y. Partials we can get directly. This is a polynomial. It's actually a nice polynomial. It's a quadratic form. That is. We've got 2x plus 3y, and dz dy is 3x minus 2y. All right. So those are nice derivatives, and what do we want to do here? The total derivative actually ends up being a function of not just x and y, but also delta x and delta y. So we need those values as well. I can write those down here. What is delta x? It's the difference between the slightly varied values and the original values. So this is 0.05, and delta y is minus 0.04. Okay, and we're going to go ahead and plug those in for delta z, and at the points 2, 3 for our derivatives here. So we've got 2 times x plus 3y delta x plus 3x minus 2y delta y, and like I said, plugging everything in, we get 2 times 2 plus 3 times 3, and then delta x we know is 0.05 plus 3 times 2 minus 2 times 3, and times minus 0.04. Well, conveniently, this term cancels out because that's 0. And now we have 4 plus 9 is 13, and 13 times 5 is 65 over 100. All right, and so that is our approximate error in z. And so z itself should be, let's see, z, or maybe we should write f. F of 2.05, comma 2.96 is going to be our original z value, f of 2.3, plus this delta z now. So f of 2.3 is, well, what is it? It's plug 2 and 3 into this function, and we get 4 plus 18 is 22 minus 9, and that is 13. So we have 13 here, and then plus our 65 over 100, right? All right, and this gives us 1300 plus 65 over 100, which is 13.65. Okay, so that's pretty darn good. And let's compare this to our delta z. So delta z is literally just the difference in these two things. And if you go ahead and compute that with your calculator, use like a Taylor series or something for this, minus f of 2, 3, we should get 0.6449, and so delta z would give us that f of 2.05, comma 2.96 is approximately 13.6449. And so those are pretty darn close, but one of them is a little bit easier to compute. This one requires taking derivatives, so it's actually the harder one. Okay, so let's go ahead and finish our last problem here. We're given the base radius and height of a right circular cone are measured to be 10 plus or minus 0.1 centimeters and 25 plus or minus 0.1 centimeters. Find the maximum error in volume computed using these values. Okay, so first off, we have to write down the formula for the volume of a cone, a right circular cone, in terms of its radius and height. And if you don't know that, it is just like a cylinder, except it has this factor of 1/3 in front. Okay, so basically what we need for the maximum error is the differential. So we need delta v, and this is partial v, partial r, no, not delta, little delta r, plus partial v, partial h, little delta h. All right, let's get our little delta values first this time. So these are going to be 0.1 centimeters, and okay, that one's also 0.1 centimeters. And the derivatives are going to be partial v, partial r equals 2/3 rh. Partial v, partial h is 1/3 r squared. All right, so now that we have our derivatives, we can plug in some numbers. And what numbers do we want to plug in? Okay, so we'll have R equal 10 centimeters. This is our sort of base value, what we think the measurement is, and H 25 centimeters. And so now we can compute our error, delta V, by just plugging everything in. So we have 2/3 times 10 times 25, now times delta R, which is 0.1, or divide by 10. So these two factors cancel out. And then we add on partial V, partial H at 10. So we have 1/3 times 100 is 10 squared. And last, our delta H is also 0.1. So we get some cancellation here as well, but we only lose 1 0 instead of both. And so our final answer here is 25 times 2/3. So let's pull out that 1/3. We have 2 times 25 plus 10. So that is going to be 60 over 3, 30, which is 20. And so 20 centimeters cubed is our approximate error. Note this is not the value of the volume, not volume. So this is just how far off our volume measurement might be from the actual value. So we can go ahead and compute what we think the volume is going to be. 10 squared is 100 times 25. And this is 2,500 over 3, which is 833. 833.33 and so on, whatever. And this would be centimeters cubed. And so we think that this, given our measurements, is at most 20 centimeters cubed off. All right, and that is it for our examples.